class in Calculus 3. For today, we will take an application of double integral or double integration to finding the area of a region in the plane. And we take now our first example. This is the region whose area we want to find by double integration. It's a triangular area in the plane or xy plane. But using the formula for finding the area of right triangle, we can find the area of this right triangle, and then we will check the result using double integration. Using the formula for area of right triangle, the area is denoted by capital A and is equal to 1/2 BH. You can take the base as the side of the right triangle, or you can take this base as this side of this right triangle as the base. We take this side of the right triangle that coincides with that lies in the y-axis as the base. So the base of that right triangle is 2 units. From 0 to this point is 2 units. And the other leg of the right triangle, which is this side of the right triangle, becomes the height. And the height is 3 units. From this point up to this point is 3 units. And substituting the values of the base and the height of the right triangle, we get 1/2 multiplied by the base, 2 units, multiplied by the height, 3 units. But 2 and 2 will cancel out. Therefore, the area of this region R is 3 square units. And to find the area of a plane region or a plane or a region in the xy plane, this is the formula that you will use using double integration. For finding the area of a plane region, this is the formula that you will use. You integrate with respect to y and then with respect to x over the region R. And there are 2 ways by which you can apply this formula. One way is to get a vertical rectangular strip or vertical element from the region R. And if you do that, you will integrate first with respect to y. Or you can get the other way is to get a horizontal rectangular strip or horizontal element of this region R. And if you do that, you will integrate with respect to x first, and the variable y is to be held as a constant. I will do the first method by taking a vertical rectangular element or vertical strip from the region R. If you use a vertical strip, as I will now illustrate, we will integrate with respect to y first, and we hold x as a constant. And the value of y will vary from the y at this point to the y at this point. The y at the lower base of the rectangular element to the value of y at the upper base of the vertical strip or vertical rectangular element. And that would be the limits of the integration when we integrate with respect to y. The value of y will vary, or the limits of the integral sign will vary from the y at this point to the y at this point. And we start with the upper limit of the integration with respect to y, which is given by the value of y at this point. And at this point, the value of y is 2. At the lower base of the vertical strip, we have to find the value of y. But you can see this point is a point on this line. And the line passes through the origin, or the point 0, 0. And this point with coordinates 3 and 2. We first find the equation of the line through these points 3, 2, and the origin, or the point 0, 0. Since we know that this line passes through 2 points, we can find this equation from your analytic geometry by using the 2-point form of equation of a line. The 2-point form of equation of a line is given by this formula. Y minus y1 equals y2 minus y1 all over x2 minus x1. And this ratio of the change in y values to the change in x values is actually the slope of the line and is multiplied by x minus x1. And the first point with coordinates x1 and y1 may be taken as the origin, or this point. I will take the origin as the point x1, y1. So if we take the origin as the first point, the second point with coordinates x2, y2 will be the point with coordinates 3, 2. And we simply substitute these values of x1, 0, y1, 0, x2, 3, y2 is 2 into this 2-point form of equation of a line, and we solve for y in terms of x. Y minus y1, y1 is 0. Is equal to y2 minus y1, y2 is 2 minus 0. All over x2 minus x1, x2 is 3 minus x1 is 0. Multiply by x minus x1, and x1 is 0. We simplify y minus 0 is y equals 2/3 multiplied by x. X minus 0 is x. Hence, we integrate with respect to y and evaluate the result from the y at this point, 2/3 x, to the y at this point, 2. And then we integrate with respect to x, and the value of x will vary from 0 to 3. Integrating with respect to y, integral of dy is y. And we evaluate y from 2/3 x to 2. And to evaluate, we start from the upper limit. We start with y is 2. When y is 2, replace y with 2, you get 2. Minus when y is 2/3 over x. Simply replace y with 2/3 minus x. Now we integrate with respect to x. And this is actually the difference, 2 minus 2/3 x is actually the height of this rectangular element. This vertical strip or vertical rectangular element from region R. So the height of this vertical strip is equal to 2. The value of y at this point minus this height, which is given by 2/3 minus x. And if you will find the area of this region R by a single integral or single integration, and you will take a vertical strip or vertical rectangular element. This is the single integral to evaluate. The area of the rectangle is, the area of this rectangular element is equal to the length, which is the height of the rectangle, multiplied by the width, which is dx. So this is height. The length multiplied by the width. The length is the height of this rectangular element, 2 minus 2/3 x, and the width is dx. But this was obtained from this double integral formula for finding the area of a plane region using double integration. Now we evaluate, we integrate this expression with respect to x. The integral of 2 with respect to x is 2x. Minus the integral of 2/3 x with respect to x. 2/3 is a constant, or minus 2/3 is a constant. So we actually integrate x only, and the exponent of x is 1. And by power rule, the integral of x is x squared over 2. And the denominator, the 2 in the denominator will cancel out with 2 in the numerator. Hence, the integral of minus 2/3 x is negative x squared over 3. And we now evaluate this result from 0 to 3, beginning with x equals 3. When x is 3, you get 2. Multiply by 3 is 6. Minus when x is, we substitute x also for x squared. When x is 3, you get 3 squared, 9, divided by 3 is 3. Minus when x is 0. When x is 0, you get 2 multiplied by 0 is 0, minus 0 squared over 3 is 0. 0 minus 0 is 0. And you can see that the area we get using double integration is 3 square units, which is the same as the result we get using the formula for finding the area of right triangle. Now we find the area of the same plane region R using a horizontal straight or horizontal rectangular element. Using a horizontal strip or horizontal rectangular element, you now integrate first with respect to x and you take y as a constant. And the second integral from the left will have limits for values of x from the value of x at this point to the value of x at this point. And the value of x at this point is 0. And the value of x at this point we find using the equation of the line, because you can see this point at this side of the horizontal rectangular element is a point on the line with the equation y equals 2/3 over x. And we solve for x from this equation. We multiply 3 by y, cross multiply, you get 3y equals 2x. And dividing both sides of this equation, 3y equals 2x by 2. You get 2x divided by 2 is x equals 3y divided by 2 is 3y over 2, or 3 halves multiplied by y. So at this point, the value of x is 3 over 2y. And at this point, the value of x is 0. So we set the limits of the second integral from the left from 0 to 2 to 3 halves y. And we first integrate with respect to x, then with respect to y. And the value of y will vary from 0 to 2. First integrate with respect to x, the integral of dx is x. And we evaluate x from 0 to 3 halves y. After we evaluate, we integrate with respect to y and evaluate the result from 0 to 2. We start with the upper limit. When x is 3 halves over y, simply replace x with 3 halves over y. Minus when x is equal to 0. When x is 0, you get minus 0. and 3 halves y minus 0 simplifies to 3 halves y. Now we integrate with respect to y. 3 halves is a constant, so we will actually integrate y by power rule. The exponent of y is 1, plus 1 is 2, and divide by 2. And you get 3 halves multiplied by y squared over 2. And that's equal to 3/4 y squared. And we evaluate 3/4 y squared from 0 to 2. Beginning with the upper limit, when y is 2, you get 2 squared is 4. And that 4 in the numerator will cancel out with 4 in the denominator. So you get 3. When y is 2, you get 3. Minus when y is 0. When y is 0, you get 0 squared is 0. Multiplied by 3/4 is 0. Again, we get the same area of 3 square units, but in the second method, we take a horizontal strip or horizontal rectangular element of the region R, whose area we just found and is equal to 3 square units. For our second example, consider the following region. The region R is a semicircle in the xy plane with center at the origin or the point 0, 0, and the radius of the semicircle is A units. And we can actually find the area of the semicircle using the formula for the area of a circle. The area of a circle is given by pi r square, where r is the radius, and in this region R, the radius of the semicircle is A. But this is for the area of the whole circle, and we only want the area of half of a circle or semicircle. So the area of this region R is 1/2 of the area of the circle with radius R. And substituting the value of R, the radius, the area of the region R is equal to 1/2 of the area of the circle. Pi R is A to the power 2. A to the power 2 is A squared multiplied by 1/2, 1/2 A squared multiplied by pi, square units. Thus, the area of the semicircle is 1/2 A squared pi. Now, we will find the area of the semicircle using double integration and taking a vertical strip or vertical rectangular element from region R. If you use a vertical element or vertical strip of the region, the given region, plane area, the formula to use to calculate the area of R is given by the following. As I said earlier, we integrate first. If we are using a vertical strip, we integrate first with respect to y and then with respect to x. So we set the limits of the second integral from the left. for the values of y for the values of y at the lower base of the vertical strip to the value of y at the upper base of the vertical strip. Now, the area of a circle with center at radius r and with radius a and center at the origin is given as follows. From your analytic geometry course, the area of a circle with center at the point HK and radius r is given by this form. This is called the center radius form of equation of a circle. In our example, the center HK is the point 0, 0 or the origin, and the radius r is equal to a units. Thus, the area of this circle with center at the origin and radius a is given by x squared plus y squared equals a squared. Because h is 0, x minus 0 is x minus 0 is x to the power 2x squared plus k is 0, y minus 0 is y to the power 2y squared equals the square of the radius r is a. And from this equation, for the vertical strip, we want to set the limits of this integral from the value of y at this point, the lower base of the vertical strip, to the value of y at this point. So from this equation of the circle with center at the origin and radius a, we solve for y. And to solve for y, we start by transposing x squared to the right-hand side. We transpose x squared to the right-hand side, or we subtract x squared from both sides of the equation, and we get y squared equals a squared minus x squared. If you subtract x squared from the left, x squared will be cancelled from the left, and you subtract the same minus x squared. Subtract the same x squared from the right, you get a squared minus y squared. And now we get the root of both sides. We extract the root of both sides to solve for y. And the root of y squared is y equals to the root of a squared minus x squared. And we know for a fact that a positive real number has two roots, the positive root known as the principal root and the negative root. And so we specify that y has two values, the positive root of this expression and the negative root of this a squared minus x squared. The lower base of the vertical strip, which is a point on the semicircle, and this point is below the below the x-axis. So the value of y at this point is equal to the negative of the square root of a squared minus x squared. At the upper base of the vertical strip, which is a point on the semicircle, and the point is above the x-axis, the value of y at this point is given by the positive root, or simply the square root of a squared minus x squared. As we set the limits, the lower and upper limits of the second integral from the right to integrate dy. the lower limit will be minus square root of a squared minus x squared. And the upper limit is square root, the principal root of a squared minus x squared. We integrate with respect to y first and then with respect to x. And the limits of the integral sign when we integrate with respect to x, the value of x is from 0 to a. Integrating now with respect to y, the integral of dy is y. And we evaluate y from the upper limit, y is square root of a squared minus x squared. We evaluate y from negative square root of a squared minus x squared to positive square root of a squared minus x squared. But when you evaluate y, you start with the upper limit. So replace y with square root of a squared minus x squared. Minus when you replace y with negative, minus negative is square root of a squared minus x squared. But this negative times negative is positive. And you have square root of a squared minus x squared plus square root of a squared minus x squared. It's like combining like terms and you get 2 square root of a squared minus x squared. And we integrate with respect to x. By inspection of this integrand, it suggests that we use a trigonometric substitution. And from your course in Calculus 2, Integral Calculus, if the integrand contains an expression of the form a squared minus x squared, then we use the trigonometric substitution a times sine theta. If we have an expression of the form a squared minus x squared in the integrand, we use this trigonometric substitution. We let x equals a multiplied by sine theta. And differentiating both sides of this equation, derivative of x is dx equals a times derivative of sine is cosine theta d theta. We is a constant, so we can take this out of the integral sign. We have 2 times 2 now is outside of the integral sign. So we get square root of a squared minus x squared. And we now make use of the substitution. We replace x with a sine theta. And we square it because this is x squared. Multiply by dx. dx is a cosine theta d theta. A now is equal to 2 times the integral of square root of a squared minus quantity a sine theta squared multiplied by a cosine theta d theta. And we simplify this expression. We take the squared of a sine theta. By property of exponents, we get a squared multiplied by sine squared theta. Multiply by a. Again, a is a constant, so we multiply a by 2. And we now multiply this by cosine theta d theta. We simplify further, we get 2a times the integral from 0 to a. And the radical a squared minus a squared sine squared theta has a common factor of a squared. We factor out a squared. If you factor out a squared, the other factor is obtained by dividing each of this term by a squared. A squared divided by a squared is 1 minus a squared sine squared theta divided by a squared is sine squared theta. But we can extract the root of a squared. The square root of a squared is a, and a is a constant. Multiply that by 2a. You get 2a squared. And we can further simplify this by using trigonometric identity. In particular, we apply one of the Pythagorean identities that says sine squared theta plus cosine squared theta is equal to 1. And if we replace 1 minus sine squared theta by cosine squared theta, we can extract its root. The square root of cosine squared theta is cosine theta. And there is cosine theta outside. Multiply cosine theta by cosine theta, you get cosine squared theta. And to integrate cosine squared theta with respect to theta, we make use of another trigonometric identity for the cosine of twice an angle. We now simplify further this integral. We use an identity, Pythagorean identity, that is equal to 1 minus sine squared theta. One of the Pythagorean identities from your course in plane trigonometry says that the square of sine plus the square of cosine is equal to 1. And we transpose sine squared theta to the right hand side, or we subtract sine squared theta from the left and from the right. If you subtract sine squared theta from the left, you will get what is left at the left hand side is cosine squared theta. And we subtract the same quantity from the right, 1 minus sine squared theta. And the area now of the region becomes 2a squared times the integral from 0 to a of the square root of, we now replace 1 minus sine squared theta with cosine squared theta. Square root of cosine squared theta. Multiply by cosine theta d theta. But the square root of cosine squared theta is cosine theta multiplied by cosine theta d theta, and we get cosine squared theta d theta. And cosine squared theta d theta is not readily integrable, so we now make use of another trigonometric identity for cosine of twice an angle. The cosine of twice an angle, or cosine 2 theta, is equal to 2 cosine squared theta minus 1. And from this identity, we solve for cosine squared theta. We want to replace cosine squared theta with an equal quantity. So we solve for cosine squared theta from this trigonometric identity for cosine of twice an angle. We transpose minus 1 to the left, or we add 1 to both sides of the equation. If you add 1 to the right hand side, you get 2 cosine squared theta. And we also add 1 to the left hand side to maintain the equality of the two quantities. And we now divide both sides by 2. Hence, cosine squared theta is equal to cosine 2 theta plus 1 all over 2. We now replace cosine squared theta with cosine 2 theta plus 1 all over 2. But 2 here is a constant, so 2 and 2 in the numerator will cancel out and you get a squared. Integral from 0 to a of cosine 2 theta plus 1. The second term in this sum, 1, the constant 1 is readily integrable. The integral of 1 with respect to d theta is theta. But for the integral of cosine 2 theta, we make use of another substitution. We let u equals 2 theta. This integral is now equal to a squared times the integral of cosine 2 theta with respect to theta plus 1 multiplied by d theta is d theta. And the integral of this sum is to be evaluated from 0 to a. We now replace 2 theta with the substitution. We use u equals 2 theta. We replace 2 theta with u. And we replace d theta with 1/2 du, which we obtain by getting the derivative of u and d theta by differentiating both sides of this equation. The left-hand side with respect to u, derivative of u is 1 multiplied by du. Derivative of 2 theta is 2 multiplied by d theta. And dividing both sides of this equation by 2, we get d theta equals 1/2 du. Now, since we are integrating with respect to theta, we might as well change the limits of integration for theta. These limits of integration, the original limits of integration 0 to a, are values of x from 0 to a, because the semicircle has center at the origin and radius a, so a is a point to the right of 0. When x is 0, we will find the value of theta. And also when x is a, we will find the value of theta using the substitution we used earlier. Earlier, we made use of the trigonometric substitution x equals a sine theta. And from this equation, we solve for theta, because we want to find the value of theta from when x is a and the value of theta when x equals a. We want to find the value of theta when x equals 0 and the value of theta when x equals a, because our variable now of integration is theta. From this equation, divide both sides by a. Dividing the left-hand side x by a, you get x over a. Dividing the right-hand side a sine theta by a, you get sine theta. And from this equation, we solve for theta. Theta is equal to shift sign or inverse sign of x over a. Theta now is equal to inverse sign or shift sign or arc sign of x over a. Now we find the value of theta when x is a, when x is 0. When x is 0, theta is equal to inverse sign of 0 over a. And 0 over a is 0. And what is that angle whose sine is 0? Theta equals the inverse sine of theta. Theta equals the inverse sine of 0 That means we are looking for the value of theta that whose sine is 0. And that angle in radian whose sine is 0 is 0. Hence, when x is 0, theta is 0. Now, we find the value of theta when x is equal to a. When x equals a, this becomes theta is equal to shift sine or inverse sine of a over a. And a over a is 1. Hence, when x equals a, theta is equal to inverse sine of 1. And theta equals inverse sine of 1 means that we are looking for the value for the angle theta, the value of theta in radians, whose sine is 1. And what is that angle in radians whose sine is 1? That angle is pi over 2. And you can check using your scientific calculator. Just put the mode of your scientific calculator in radians and you calculate, you check the sine of pi over 2. The sine of pi over 2 is 1. Thus, the angle whose sine is 1 is pi over 2. Now, we will have a change of limits from 0 to a to 0 to pi over 2 because our variable of integration is theta. And the area is now equal to a squared multiplied by, we now replace 2 theta with u. We have cosine of u. The integral of cosine of u. Integral of cosine of u multiplied by d theta. D theta is 1/2 multiplied by du. Plus the integral of d theta. And the integral of this sum we now evaluate from theta equals 0 to theta equals pi over 2. One half here is a constant. So the integral of cosine u multiplied by 1/2 du is equal to 1/2 times the integral of cosine u with respect to u. The integral again of 1/2 times cosine u with respect to u is equal to 1/2 times the integral of cosine u. And the integral of cosine u from your calculus 2 or integral calculus is sine u. One-half multiplied by sine u, where sine u is the integral of cosine u. Plus the integral of d theta equals theta. And since we have integrated both terms, we now evaluate this sum from 0 to pi over 2. But before we do the evaluation, we replace u with 2 theta. Because the limits now of integration are values of theta from 0 to pi over 2. This becomes 1/2 times sine u. U is equal to 2 theta. 1/2 times sine of 2 theta. Plus theta. Evaluate from 0 to pi over 3. And to evaluate this sum, we start with theta equals pi over 2. When theta equals pi over 2, you get 1/2 times sine of 2 times pi over 2. 2 times pi over 2 is simply pi. So when theta is pi over 2, the first term is 1/2 times sine of pi. Plus theta equals pi over 2. Next, minus when theta equals 0. When theta equals 0, this becomes 1/2 times sine of 2 times 0. 2 times 0 is 0. Hence, when theta is 0, the first term becomes 1/2 of sine 0. Plus theta equals 0. Plus 0. Now, if you want to make use of your scientific calculator, you put the mode of your scientific calculator to radians and you calculate sine of 0. And sine of 0 is equal to 0 multiplied by 1/2 is 0 plus 0 is 0. Also, the sine of pi is 0 and sine of pi is 0 multiplied by 1/2 is 0 and 0 plus pi over 2 is pi over 2. Hence, what remains in the quantity in this difference is simply pi over 2 multiplied by a squared. You get 1/2 a squared pi. And this is the area we get earlier using the formula for area of a circle. The area of the given region R, which is a semicircle with center at the origin and radius A, is equal to 1/2 a squared pi. And you can see that it is much easier to find the area of the semicircle using the formula for area of a circle. But this only shows that there is always other way to calculate the area of a plane region, such as the semicircle in our example 2, and that is by using double integration. For your practice, please try the following exercises. Find the area of R. R here is a plane area in the xy plane or Cartesian plane using double integration. Number 1, this exercise 1 is similar to our example. Find the area of this right triangle. And you may want to first find the area of this right triangle using the formula, which is 1/2 of the base multiplied by the height. And then find the area of this region using double integration. And you may use either a vertical strip or a horizontal strip. Number 2, also find the area of this region, which is a triangular region or triangular plane region in the xy plane. If you want to first make use of the formula for area of right triangle, you if you take this as the base, do not take the base as negative 2 units. Take its absolute value, the base would be 2 units. The negative here only indicates that this point is below the x-axis, but the base of the triangle is positive 2 units. And if you take this as the base of the triangle, this would be the height of the triangle. But when you use double integration to find the area of this right triangle, you take the values negative 2 and 3 as it is. You take negative 2 as it is when you set the limits of integration, and 3 as it is when you also set the limits of integration. And for number 3, this is our example 2, a semicircle with center at the origin and radius A. In our example 2, I made use of a vertical strip. Now you make use of a horizontal strip and find the area of this semicircle using double integration, and you should get 1/2 a squared pi square units. And that completes our lesson for today, the first part of the application of double integration. If you have questions about the lesson today, you ask your questions in the comments below. Thank you for joining me in my class today in Calculus 3.